Hello everyone, I am Muhammad Al-Sharif, the corresponding author of this study, presenting our work titled Packet Drop Rate Minimization with Age of Information Constraint in an Energy Harvesting Cognitive Radio Network. In this paper, we present a scheduling policy for two users, one transmitting status update packets and the other handling deadline constraint packets. Both operate in a spectrum sharing environment where one user has no power source and depends on harvested energy. This research was conducted in collaboration with my professors from Egypt, Professor Ahmed Abdelmalik and Professor Wahid, and from Alexandria University, Professor Sharif Rabia. Thank you for your attention and I look forward to your insights during this VTC 2024 session. Here is an overview of the content included in our presentation. We will start with the introduction, which includes an overview of time-critical application needs in Internet of Things networks, an overview of relevant studies, the motivation behind our work, and our contribution. Timely data delivery is crucial in IoT networks for applications like vehicular networks and cloud computing. Consequently, data freshness is essential for effective monitoring. The age of information measures the time elapsed since the freshest received packet was generated. Thus, a lower age value signifies more current and accurate knowledge of the source status. However, age of information is insufficient for quantifying deadline constraint traffic, as data are discarded if they exceed their deadline. Applications like healthcare monitoring, vehicular networks, virtual reality, and augmented reality depend heavily on meeting these deadlines. Thus, minimizing the average drop rate is crucial for effective performance of these applications. Moving forward, IoT networks encounter various challenges. This work addresses two primary issues. First, the cost and replacement difficulties of device batteries, which can be mitigated by energy harvesting. Second, spectrum scarcity, which we address through cognitive radio technology to optimize utilization. Before initiating this work, we conducted a literature overview and identified 5 crucial features. These studies focused on 2 key traffic types: deadline constraint traffic and status updates. Users with these traffic types may have limited power or no power sources, making energy harvesting technology beneficial. Additionally, these studies explored spectrum sharing environments. In reference 5, the authors consider regular data with no deadline. In 6, only regular data are addressed in non-spectrum sharing environment. In 7 and 8, both types of traffic are addressed with no power limitations considering non-spectrum sharing environments. In 9, only deadline constraint traffic was assumed without addressing energy harvesting technology. The most relevant research to this work is our previous study, reference 10. The importance of the mentioned features drove us to include them in our work. Building on prior studies, we focus on timely information exchange, specifically status updates and deadline constraint packets in IoT networks. We also explored the benefits of spectrum sharing and energy harvesting technologies. Our objective in this study is presenting a scheduling policy to minimize packet drop rate while minimizing data freshness for status update packets. We assumed random arrival for deadline constraint packets in contrast to our previous work that assumed deterministic arrival of data. Moreover, we derived the success probability formula within the underlay mode for the secondary user in presence of multiple primary receivers. Finally, we incorporate energy harvesting for some of the secondary users. Next, we explore the adopted system model. We have a cognitive radio network with a single channel for one primary user labeled S0 that transmits data to multiple receivers. The secondary system contains 2 secondary users. S1 sends deadline constraint data where packets arrive according to a Bernoulli process, and this secondary user has a dedicated power source. S2 sends status updates and doesn't have a power source but harvesting energy from the environment following a Bernoulli process. G represents the channel gain between the transmitters and the receivers. Let H represent the primary user channel state at time t and takes the value 0 and 1. The value 0 indicates that the primary user is ideal and 1 indicates that the primary user is active. We assume perfect channel sensing case, all the links experience relay block fading, and model the primary user channel activity as a two-state Markov chain with the shown transition probability matrix. The scheduling decision is labeled by U of t and indicates whether to schedule S1 or S2, and at most, only one secondary user is selected for transmission. The power is allocated to the secondary users based on the scheduling action and the channel state as shown. Due to the uncertainty in our adopted environment, a packet may be delivered successfully or not. The I of t is a binary indicator that equal to 1 for successful delivery of the packet and 0 otherwise. This probability depends on the channel state. For example, if the primary user is ideal, this equals to bi given I, which means that the secondary user I transmits alone. Conversely, bi given I and 0 means that it transmits with the primary user. Therefore, we need to calculate these probabilities. Using the formula for the SNR at the secondary receiver, the probability of success when the primary is ideal was obtained in reference 12. For the case when the primary user is active and there are multiple primary receivers, using the SINR formula, we obtained the success probability formula. Next, we explore the users of the secondary system. For the deadline constraint secondary user, packets arrive at the S1 queue following a Bernoulli arrival process with probability of lambda. Each packet has an equal deadline denoted by M. Its queue evolves according to the following equation, where the capital is the indicator for the dropping event of an expired packet, and alpha is the indicator for the packet arrival. Note that S1 can only be scheduled if its queue is not empty. For the status update secondary user, its battery level evolves according to the following equation, where Xi is the transmit power of S2, E is the energy packet arrival indicator, and gamma is the conversion factor from the harvested energy unit to power in milliwatt. And an update packet can be sampled at any time with certainty. The age value is updated as shown, where B of t indicates that the battery level is greater than the required transmit power. If S2 is scheduled for the successful delivery, the age is dropped to 1, otherwise it's increased by 1. Noting that S2 can only be scheduled when B of t is equal to 1. Next, we investigate the problem formulation section. Our objective is to minimize the average drop rate for the deadline constraint secondary user subject a time average age of information threshold for the age-oriented secondary user. Note that the expectation in the problem is calculated with respect to the randomness of the environment and the scheduling action, recalling that the capital of T takes the value 0 or 1. But we need to quantify the taken action based on the remaining time slots before expiration. The function f of t was proposed in reference 8 for this purpose under the certain transmission assumption. In this function, m is the deadline for the packets and n of t is the remaining slots before expiration for the head of the line packet at the current slot. Thus, we develop a stochastic function denoted by C1 to account for the uncertainty in our work. If the deadline secondary user is not scheduled, meaning that U1 is 0, C1 equals F. However, if U1 is 1, C1 depends on the random variable D1, recalling that D1 is a successful delivery indicator. Hence, the objective function in the optimization problem shifts from minimizing F to minimizing C1. This is a constrained optimization problem. Next, we examine the drift plus penalty section to solve this constrained optimization problem. Our scheduling policy is obtained using the drift plus penalty technique, which converts the formulated problem into a constrained optimization problem. This is done by turning the constraint into a queue stability condition. First, a corresponding virtual queue is constructed. According to the strong stability condition, the constraint is satisfied by ensuring the stability of this virtual queue. To stabilize the queue, we define a Leibniz function L of t, which is the square of the virtual queue backlog. Then, the system state is defined as shown. Next, by finding the conditional expectation of the change in L, known as the conditional drift, we derive the drift plus penalty expression. This expression is minimized per slot to stabilize the queue and reduce the average drop rate. The parameters named V controls the trade-off between these two targets. Due to the complexity of the exact drift plus penalty expression, we derive its upper bound. Terms unaffected by the scheduling action are then neglected. Then, the resulting upper bound is minimized. Finally, based on the visible actions and the system state at the current time slots, the value of the objective function can be calculated. In summary, the steps for implementing the proposed policy are outlined in Algorithm 1. To start, the components of the system state are initialized and the value of V is selected. The scheduler observes the system state and behaves greatly to minimize the cost function at the current time slot. Next, the system state components change based on the taken action. The channel state is updated and the steps are repeated starting from step 2. Moving to the simulation results section where the performance of the obtained policy is evaluated. Simulation runs are conducted for 100,000 slots using MATLAB. The parameters are set as shown in Table 1. For comparison purpose, we propose a greedy baseline policy that gives priority to the edge-oriented secondary user to ensure the constraint is satisfied. First, the average age up to the current time slots donated by a t-bar is calculated. If it's greater than delta max, indicating that the constraint is violated, S2 is scheduled if it has enough power. If not, the deadline secondary user is scheduled if its queue is not empty. Otherwise, neither of them is scheduled. In Figure 2, the average drop rate and the average age are examined against the drift plus penalty parameter V. As we see, increasing V puts more emphasis on minimizing the average drop rate. However, this also increases the virtual queue size, leading to a higher average age value. Despite this, there is no violation of the constraint. Next, the effect of the arrival rate of the harvested energy on the average drop rate is investigated. At the beginning, the harvested energy is insufficient to meet the constraint. As the arrival rate increases, the percentage of scheduling the edge-oriented secondary user rises. However, this impacts the average drop rate. As the arrival rate increases and the energy becomes sufficient, the constraint is met and the drop rate decreases. Further increases in the arrival rate have minimal effect on the average drop rate. We also observe that initially, the proposed and the baseline policies perform similarly. However, as the rate increases, a gap between their performance emerges. Finally, the influence of the primary user transmit power on the drop rate is examined. We notice that increasing primary user transmit power decreases the probability of success for the secondary user within the underlay mode, leading to more expiration and dropped packet. If the deadline is raised, packets can wait longer in the queue, resulting in a decline in the drop rate. The figure also illustrates that at lower value of the primary user power, the baseline policy has a performance close to the proposed policy. However, as the power increases, a larger gap between their performance emerges. To conclude, let's move to the conclusion section. In this work, we obtained a scheduling policy for two secondary users, one with deadline constrained packets and another with status updates that has energy harvesting capabilities. These users operate in a single channel cognitive radio network under the interweave underlay access scheme. The policy aims to minimize the drop rate of the deadline constrained packets while maintaining data freshness for the status update stream. The results showed how energy availability and primary user transmit power impact the drop rate. Results also demonstrate that insufficient energy hinders constraint fulfillment. The proposed policy outperformed a threshold-based policy, demonstrating the effectiveness of dynamic scheduling. At the end, this paper is based upon work supported by Science, Technology and Innovation Funding Authority (STDF) under grant number 48186. Professor Sharif Rabia is the project PI. Thank you.